I'm very pleased to have you all today. So we are here together to attend the PhD defense of John Nicot. So for those who want to know who is who, so here in local, you have Professor Christophe Gégaud, who's going to be the chairman of this board, Professor David Fadel, and myself, who were the supervisor and co-supervisor of the PhD. And then online, we have Professor Vincent Frick from the University of Strasbourg. We have Jean Ménéquens from UNOC, a company in Toulouse. Jan, and we have Professor Mirabalsi from the University of Vancouver. So now I'm going to let our chairman organize the starting, and thank you all for being there. So Christophe.
Okay, thanks a lot, Jerry. Thank you for the presentation of the different member of the jury. Now you can start the PhD presentation. John, you have 45 minutes for this presentation. In the second time, we have a question session for the different points of your contribution.
Okay, thank you, Mr. Chairman. So we will begin. Let me just check, is the PowerPoint working?
Yep.
Okay, so let's start. So today we'll be defending my thesis entitled The Remote Powering of Wireless IoT Nodes under the supervision of Mr. Taris and Mrs. Fadel. So the outline of this work will be, first of all, to introduce wireless power transfer, introduce system modules of the node I have developed, analyze it, see how it works with different scenarios of application, and then conclude. So humankind has an increasing value and attachment to technology with greater and greater interdependence. This is used to provide convenience and optimize our time and resource usage. So these advancements will generally continue across time. So the world is generally going to be more connected as we explore our relationship with technology. So this brings us to the Internet of Things, which has numerous applications, including smart homes, smart cities, different wearables, RFID tags, asset management, agriculture, everything. It's a huge, huge domain. So there's been a large demand in IoT in the recent years. I mean, we're talking about billions of devices here, billions, absolute huge numbers, and it just keeps on growing and growing and growing. Generally, classical powering methods for devices involve the use of batteries, which require maintenance, and wires, which can give us mobility and location constraints. So the future of IoT, since these devices have to be mobile and easily adaptable, should avoid these if necessary, because it will be complicated otherwise. So the solution to power all these IoT nodes is using on-site environmental energy extraction, which is also called energy harvesting, using different sources available in the environment. We will be interested mainly in radiant sources, which include RF sources, which are human-made and can be turned on and off on demand, as well as solar sources, which generally depend on inside lighting and sunlight. So what is WPT, or wireless power transfer? Basically, there are two electromagnetical physical phenomena, near-field EM and far-field EM. We will be interested in far-field EM. Why? Because in the RF 900 megahertz and 2.4 gigahertz ISM band, the distance at which far-field begins to operate is around 10 to 50 centimeters. And if we're considering IoT, for instance, in a household, the nodes will always be greater than this distance away from any base station. So the IoT node is in far-field conditions. So a brief history of wireless power transfer. First of all, it started off with Nikola Tesla's dreams and experiments in the late 1800s. So he started off with some inductive coupling experiments to show wireless power transfer, and also progressively moved on to a couple of long distance tries. And generally, at the end of the 19th century and in the beginning of the 20th, wireless power transfer was put on hold as people started discovering the radio and transatlantic communications. So it was kind of put in a little box and hidden away. Until the 1950s, in which several civilian and military experiments started popping up, notably the work by Mr. Brown, who worked on a wirelessly powered helicopter with about 5 kilowatts of transmission energy, and the NASA Goldstone experiment, in which they sent half a megawatt of energy 1.5 kilometers away with 6.8% of efficiency. Notably, the frequencies at which these devices operate are in the same range as the 2.4 gigahertz ISM band. So today, briefly resuming that, in the late 1800s, it was experimentation, 1900s, communications, mid-1950s, high-energy WPT, and today we're looking to have wireless power transfer in a more decentralized, adapted manner. So a brief overview of this work is to reconcile the energy needs and IoT by using energy harvesting, to present an IoT node, so its design, manufacture, testing, and analysis, to model the node, and to apply it to different scenarios of operation to determine its performance. Moving on to section 2, which is system modules, we will be looking, first of all, at the rectifier that is present in the node. It is comprised of an N-stage architecture. The sensitivity of the rectifier generally increases with the number of stages, N. However, its efficiency generally decreases, especially at lower power levels. Matching rectifiers for optimal energy transfer in the RF domain is somewhat difficult, and it's reactive to P-in, mainly because rectifiers or Schottky diodes have a very high capacitance, and it's always in the edge of the Smith chart, which is hard to deal with, which could also be a problem with industrial applications in which repeatability is required. Power output delivered by a single-stage rectifier at 0 dBm can be around half a milliwatt, which is not bad. But for more realistic conditions of around -15 to -25 dBm, we might be looking at maybe a microwatt or two to about a dozen microwatts. So the range of interest for this application is -25 to -15 dBm, which corresponds to the power that would be received by a node at a distance of several meters away from a 1-watt source at 900 megahertz. For the purposes of this work, we have chosen the Greinacher topology for each of these stages due to its superior performance to other stages as presented in the previous slide. So the node can receive RF power. Moving on, now we want to look at solar energy. So for solar energy, we've just used some generic monocrystalline solar panels, which present an efficiency under full sunlight of around 20%. It most certainly gives us a lot more energy than wireless power transfer itself. We generally can easily go from tens of microwatts to milliwatts. It can be used indoors or outdoors. And of course, the efficiency drops with luminosity and is also affected by the source of light. For the scenarios in this work, we will be using a worst case scenario of 100 to 500 lux. This would be the case if the node was, for instance, located indoors. So the node can receive solar energy. Now that we've gotten energy, we have to store it somehow in order for it to be used at a later date. So we will be using two types of storage elements, or rather one type with two subtypes. The supercapacitor for solar power harvesting, and the ceramic capacitor for wireless power harvesting. So for the wireless power harvesting, why do we use ceramic capacitors? Because they are small in size, so they can easily be charged with lower power levels, and they have a low leakage current in the hundreds of nanoampere range, usually, for the ones we've used. So it's best to use these to store small amounts of energy without too much loss. For solar harvesting, we're going to be using supercapacitors. Why? Because they have a large amount of energy they can store, and with the high amount of energy solar power can deliver, they can easily be filled up. However, their leakage current is a bit more problematic, though they can still provide a large degree of autonomy to the node. So we can now store energy. So now that we've dealt with getting energy and storing it, we have to figure out how to manage this energy. So it's a question of supply and demand. Energy is generated and stored. So how do we reconcile this? How do we optimally extract energy from the node? Well, we're not going to use the classical method of just sending the energy into a storage element into the load. We are going to use a power manager. So a power management module will be inserted between these different devices, and this will permit optimal extraction of energy from the source, optimal methods to store the energy, and provide optimal amounts of energy to the load. We will be using boost converter-based modules for this work, and the use of maximum power point tracking in these converters. So maximum power point tracking is basically each device or energy source has a load curve, an IV curve, and the power available is basically the current at the load point times the voltage, which depends on the load applied to the energy source by whatever is taking in the energy from this source. So if there is a mismatch or incorrect load applied to it, then we will have less power available for the node. So this is important in order to extract energy. So for this, we have determined the MPPT parameters for the boost converter we used. For RF, the RF rectifiers that we have used, generally in terms of sensitivity or open voltage, the optimal load configuration for the device is around 30 to 40%. And for solar, it's around 60 to 70%. The power management modules also have a buck converter, which powers the node at 1.8 volts. It has a high efficiency when the node is operating, but a lower efficiency when the node is sleeping, because when the load current is low, the buck converter tends to have poor efficiency. To share the energy between the solar energy harvesting and the rectifier, or the wireless power harvesting, we use a passive method using a Schottky diode, so that if there is surplus solar energy, it will go and charge the rectifier, the wireless power transfer, energy storage device. And if not, then if there's only wireless power available, then it will not, the wireless power storage will not flow back into the solar energy storage. So now we can use the harvested power. Okay, so now we've dealt with energy, so now we have to start dealing with functionality. So first of all, we have to receive messages so that the node can do something. So for this, we use a radio demodulator, which can receive OOC or ASK modulated RF data. The actual circuit itself uses a data slicer with a high-pass filter. The outgoing voltage that is being decoded by this demodulator is normalized to be given to the functionality module of this node. And a wake-up generation is also implemented so that the node can actually wake up and process the command when required. The message format we have chosen for this is in two parts. There is a synchronization signal in order to start up the data slicer and to wake up the node, and an actual message which contains the commands that the node, or the command that the node will have to process. The demodulator has a sensitivity of about -31 dBm, which is not bad, and a power consumption of 750 nanowatts, which is static. So the node can listen for instructions. When the node receives instructions, it would be nice to actually do something in terms of sensing. So we have received an instruction, and the IoT node is all about measuring things. So now we have to look at what we can do to measure environmental parameters. So we will measure environmental parameters using different types of sensors. So we can measure pressure, temperature, luminosity, amongst other things, using different types of interfaces, which can either be analog or digital. The important thing is for these sensors is to minimize their power consumption in order for the node not work. So we will choose devices that may have a low sleep current, and if necessary, maybe even shut them off while they're not being used, as well as minimize the time spent measuring. So in terms of power consumption, during sleep, most of these sensors, they consume nothing, a couple of maybe tens or hundreds of nanowatts. During measurement, they use a lot more, easily half a milliwatt to 1 or 2 milliwatts instantaneously. And on average, for a measurement every minute, they use just under to just above maybe 1 or 2 microwatts. So low power measurements with COTS devices is possible. Now that we've gotten instructions into the node, sense the environment, it would be nice also to send them back. IoT is all about connectivity, so if we can't send any measurements or data back, it might be a little bit hard to call it IoT. So for this, we will use a data transmission module, which of course has tremendously high amounts of energy usage. As we all know, the transmission aspect of any RF system is usually the one that also consumes the most energy. The instantaneous power consumption of this module is easily in the dozens of milliamps. So we only use it punctually. So short transmissions as fast as we can. And this ensures that it can still operate with only wireless power harvesting with the ceramic capacitors. Also, we should try and send as much data per message as possible. This is because there's some overhead for the module that is always is required to send data. So by sending more data, even with this overhead, we can decrease the consumption in nanojoules per bit, depending on the length of the message. As for the actual data packet format itself, the radio is capable of emitting digital FM or AM modulations. We've used GFSK for this work. It has a variable baud rate. It can encrypt data if required and can do carrier sense multiplex accessing arbitration, which is just a fancy way of saying it will check to see if there is not going to be any collision before sending the data if someone's emitting in the same channel. It must also be calibrated on startup. The message format, which is configurable, that we have used for this work, which is 64 bits long. The synchronization section, which is 32 bits long. This is in order to do clock reconstruction. The actual data segment, and a cyclic redundancy check, which is used to verify data integrity on the receiving end. On the computer, we have, this is an example of reception of packets. We can see that packets were received. And the last byte that we see there is the temperature that the node is measured in hexadecimal. So around 25 degrees. So the node has transmission capability. Finally, now that we have all these different functionalities available to us in the module, we have to orchestrate this. So we have to put it together using a microprocessor which will tell everyone what to do, when, and how. So the capabilities of this microprocessor must, of course, be decoding incoming messages, be able to control sensors and do measurements, interface to the radio to transmit data, store and retrieve data in the FRAM. We've included an FRAM module to store data, as well as debugging, which is always something that we should consider. It is the orchestrator of functionality, as previously mentioned. It has different power consumption states. When it's sleeping, it will generally consume about 45 nanowatts. When it's woken up and processing an incoming message, the power consumption will jump up to about 400 microwatts. And when doing an actual instruction from the message, it will be greater than 400 microwatts. I mean, when we're even transmitting data, the power consumption will be higher as it sends the data into the radio module. takes about 40 to 50 milliseconds to process a message. So in terms of an overview of the actual wake-up algorithm, that is the algorithm that the microprocessor uses when it is woken up to receive a message. So wake-up is generated by the radio demodulator module. Synchronization bits are received and information about them is stored to do clock reconstruction of incoming data. Then the message is received and bit by bit, and we wait for the message to come in entirely, and then we process the received message. And if there is a problem, there will be a time. Is it working? Oh yeah, it is, sorry. And if there is a timeout at any point in this operation, then the RX will be aborted and we will go back into sleep mode. As for the actual functionality aspect, when the PIC is first turned on, it goes to sleep. Then when a wake up is received, as mentioned in the previous slide, it receives the data frame. If it is being addressed, because it is addressable and has an address associated to it, then it will process the command, such as getting sensor values, debugging, storing or retrieving data from the FRAM, and transmitting data. And once it's done, it goes straight back to sleep. So the node is intelligent. And behind the node there, you can see some of the code that was stuck into it. So in conclusion for the part 2, we have looked at different modules that are used for the development of a wireless power transfer solar IoT node, which include energy harvesting, management, storage, the functionality aspect, as well as sensing and data retransmission. All these modules were described, metrics, associated metrics are presented, measurements and results were also presented, and a brief overview of their power consumption was also looked at. So the elements of the IoT node have been characterized. Moving on to system analysis, we will now be looking at the performance of the node, or more how it is plugged in together. So we'll be looking at power consumption, interoperability, and its applicability of all this to different various measurement scenarios. We'll also specify the measurement setup that we use to measure, a simulator which was developed to simulate different scenarios before testing, as well as to compare actual results and simulated results. So move on to modular design. We've used an iterative refinement process. On the left part of the slide, you can see first versions of the node, which were quite horrible. So we moved on, made the system modular, and we can easily remove different elements and change them as required to avoid having to do circuit boards over and over and over again. We also, for power consumption, separated the modules into what I like to call analog and digital types. Analog types being anything to do with power and receiving messages in terms of the wake-up radio, because their consumption is generally static. And digital devices whose power consumption can vary wildly depending on their state of operation. So for analog devices, the power management units have similar performance and power consumption, except that the buck converter efficiency must be considered for the BQ25570 or the WPT harvester, which provides power to the node. The comparator uses a significant amount of power, actually, around 3/4 of a microwatt. And of course, the storage elements have leakage, the supercapacitor having more leakage than the ceramic capacitor. Digital devices, the consumption varies significantly for all devices. In sleep mode, this is where the least amount of power is consumed, generally in the tens or hundreds of nanowatt range. It's the most used state of the node. The node is pretty much sleeping most of the time. When the node is operating, then various devices leave and enter sleep mode and do their various things. Power consumption is high, certainly, but it is only used for small amounts of time. And, of course, the champion of power usage is the transmission module. So briefly overviewing the power consumption, different operational states of the node can be categorized either as wake-ups or sleep. Wake-ups, they can be either false wake-ups, which can happen from time to time, or regular wake-ups with command reception and processing. So as previously stated, the power consumption varies with different digital devices' operating states, and the analog device's power consumption is generally static. Moving on to simulations. So for simulations, we have basically taken the node modules and kind of determined theoretically where power flows into what I would like to call a power flow network. Devices can be categorized into 4 different types, which is to say power generators, storage elements, power management or modifiers, as well as power consumers or the load. The simulator I've developed only does power-related usage. It cannot simulate functionality. And these simulations will be used to check the node's performance in what I would like to call a user-defined external scenario, or a scenario which is basically user-defined external conditions. So environmental conditions and user stimuli. To briefly present the simulator, we will just look at how it works. So basically, information is inputted into the simulator. So this would be how we want to configure the environment and user input. All these devices are initialized. And then every delta t increment or time increment, we calculate how much power is generated, used, or modified. We calculate these balances. We do some pluses and some minuses. Then we update all the different states associated to the device. And while we're not done, we keep on doing this over and over and over again. And when we're done, we store the simulation results and plot them if the user wants to do that. As for the test bench, the node basically can receive data from a source. The node is also present with all its modules. And of course, there are debugging capabilities to aid in seeing what is working and what is not working. Several meters away, we have a base station, which uses software-defined radio for data powering and data transmission with an amplifier. We have a coupled transceiver for data RX. By coupled, I do mean it is in the same family as the node's TX module. All this is orchestrated by the computer, and we have also debugging capabilities. Graphically, it looks like this. So here we have the node under test. On the top is a little green blob. We have an antenna and a RF coupler splitter. Debugging equipment, including a power meter to see what power is being received by the node, and a little movable tray which lets the node move around. The base station, here we see the control computer, the data TX antenna and the SDR interface in this instance, as well as a power TX antenna, an RF power source, and an RF amplifier. So for the system analysis, we have presented the assembled node. We have also shown a detailed analysis of the node's operational states and power consumption. A test bench setup was presented. A power consumption simulator was presented, created from node data, and it accurately models the node, which is not surprising as the simulator was created from measured data. So the node now is ready to be tested, and scenarios of operation can be considered. So now we will look at these scenarios of operations in part 4. So what exactly do I define as a scenario? A scenario is a set of constraints and conditions under which the node will operate, which is basically a fancy way of saying we will tell it how it's going to work. So these are both environmental constraints and user requirements. The performance of the node is evaluated in both in situ and through simulations. So the simulations were, of course, tested with the simulator, and in situ applications were measured with the test bench. The results were interpreted by the metrics as required by the scenario constraints, which means that the scenario basically was a question of, can the node do this? So the results depend, of course, on how we're going to answer this question. Scenario 1 involves the continuous RF operation of the node. So how much RF energy do we need so that the node keeps about the same amount of energy and keeps on operating? This is being categorized into two sub-scenarios. First of all, in which we will suppose an instance in which there is not a lot of power and the node only receives instructions and does not retransmit data, and an RX TX operation in which the node can receive commands and subsequently retransmit data as a result of those commands being processed. So, of course, RX TX mode consumes more than RX mode because in RX TX mode we are retransmitting data. There is a hard limit of negative 15.1 dBm on the node's input, which is basically the sleep current. You don't power enough for the sleep current, the node will eventually shut off. Simulation is in agreement with the measurements. So what does this give us? It basically means that for a 1 minute measurement interval, so a command sent to either store the data or request the data back every minute, will operate at negative 12.2 dBm for reception only and negative 9.1 dBm for RxTX. Looking at this in a little bit more detail, what would be the amount of energy required to maintain operation if we keep on adding sensors to the node? Well, power consumption, unsurprisingly, increases with the number of sensors. We still trend towards that negative 15.1 dBm hard limit. The advantage of this is that we can also see that the sensors also have low sleep currents because no matter which part of the graph we're looking at, we still trend towards that hard limit. So measurements with multiple sensors are still possible within 10 to 20 minutes at a distance of 5 meters. Scenario 2, this is fully autonomous mode operation. So how long can the node last with a fully charged supercapacitor? So we will have no solar energy and no RF energy. We will only be transmitting RF data and possibly receiving data from the node. Likewise to scenario 1, we will be having two sub-scenarios, an RX and an RX-TX mode. The hard limit which the node can survive is about 52 hours if it does absolutely nothing, which means just sleeping. This is because the supercapacitor leakage at some point becomes the biggest factor in power consumption. So 52 hours is about it for this supercapacitor that we've used. However, 24-hour autonomy is still possible with a measurement every 4 seconds in RX mode. So if we receive an instruction to measure and store some data and not retransmit it, and one measurement about every 15 seconds for RX-TX mode. So if we get a request to measure and we send it back. Looking at this, how can we improve this a little bit? Well, we've introduced something I'd like to call burst mode, which is basically, we remove now the sending of messages to the node, and we insert a small little timer, which automatically makes the node measure at an interval and sends the data back once a day with a burst transmission. So this additional simulated burst mode has better performance than RX, TX, and RX modes. Why is this? Because first of all, we are not spending so much time processing incoming messages, and we are only transmitting data once a day very fast instead of turning on the transmitter every time a message is received, sending the data, and shutting it off again. So this leads to a measurement every second, which is possible using this burst mode. Finally, scenario 3 is solar operation. So how much light do we actually require to keep the node operating? No RF power will be presented in this scenario. This scenario will assume that the node can only be charged 8 hours a day. So suppose it's sitting in an office somewhere and somebody comes in at 9 a.m. and leaves at 5 p.m., I think. Yes, 5 p.m. Based on the power produced by solar panels, operation is possible with 150 to 200 lux about. So worst case measurement intervals are, when we couple this with the previous scenario's results, is about 1.5 seconds for an RX operation, measurement interval at 150 lux, and 7 seconds for an RX-TX operation. So in concluding these scenarios, they were presented. They were used to determine possible environments the node is suited for, also to analyze the performance of the node, and as well as compare the results to the simulator. So we have a little table underneath here that shows basically a brief summary of all these. So how much power was required to operate them in continuous RF mode or a distance. And for the autonomous and solar modes, how many seconds could elapse between measurement intervals and the node could still operate. So the node can operate in different environments. So now we will be moving on to the conclusion. So as stated in the introduction of this work, there are many different IoT devices that are going to be made and are going to interact with us in the future. So we have to reconcile the power requirements of all these nodes, as well as avoiding the use of batteries, probably due to environmental or mineral resource constraints. So a WPT solar-powered IoT node was developed with a relatively small footprint. It could still be optimized, and mainly because of debugging, it was so large. It's functional, cost-conscious. We tried to drive down costs in any single way possible. It's modular, and it can maintain indefinite sleep operation at around a microwatt with either or both negative 15.1 dBm of radio frequency power and 150 lux of luminosity. A test bench was also developed to measure the node under different scenarios of operation. A simulator was developed to test hypothetical simulation scenarios of operation. The node was subjected to scenarios, so continuous RF powering, autonomous mode, and solar operation. And now we will compare it to other work. So one of the problems with such a node that crosses several different domains in electronics is that it's difficult to apply a single figure of merit to it. So we thought it would be more suitable to analyze different aspects of the node and compare them to different works, similar works, for each of these different aspects. So there are different nodes in literature that can also use RF and light sources, as well as just RF sources using only a rectifier, so a pure wireless power transfer node. Frequencies of operation of these different works that we have looked at generally also operate in the 900 megahertz to 2.4 gigahertz ISM band, as well as some other ones that also operate in UHF, so with digital television, or the 2G and 3G bands. There are also several different types of node. Our work is focused on a COTS node, so components off the shelf, which means little microchips that you will solder to boards. Though there are also ASIC devices present, so microchips that people have made and developed. Different types of load can be given after the energy management part. So we have power management, but also different work has also some functionality, sensing, and sometimes RX and TX functionality as well. Performance, also, we can compare RF and solar performance to different work. Generally, we have similar works to whatever is present in the domain. Generally, at around negative 15 dBm, RF efficiency for most work is around maybe 15 to 20, possibly 25% in some conditions, or it can operate at relatively low power levels. And for solar, generally we get between 100 microwatts to maybe up to 800, 900 microwatts at around room lighting conditions. Graphically, what do these other works look like? Well, here we have an example of a solar and radio-powered node. This is only the part that gets energy. Here we have an example, for instance, of something, another piece of work that has solar and RF energy harvesting on a flexible substrate. So it can wiggle around and possibly be put into some constrained spaces, and it's flexible. It contrarily to PCBs, which are less flexible. This was a particularly interesting example of somebody using a multi-RF power harvester. Why settle with one band when you can have many others? It uses 3G digital television and the 2G GSM bands and is quite capable in providing energy to power a node. Finally, here we have an example of an ASIC node, or at least the wake-up radio part of it. Has a rectifier, comparator, baseband processing with a small oscillator inside. So that is the RF wake-up part. Then it also has a power management unit, so a boost converter, and various associated modules that permit to give voltage to the node. Also has a small digital baseband for wake-up radio. Looking at future perspectives for this work. All right, one of the biggest problems we have encountered for this work is that COTS devices we were using are operating at the limits of their efficiency. And by limits, I do mean limits. This makes it problematic to have good efficiencies with these devices. And this could be solved by using ASICs, so microchips that you make yourself. Generally because you can make something that is more specific to the domain you're trying to exploit and therefore more efficient. ASK and UKD modulation. In a lab setting, it worked fine. In more real-life settings, there was a lot of false wake-ups because the band is congested. So a different wake-up protocol should be considered, maybe using something to do with correlators or different modulation types. The wake-up radio, and I'm not talking about the TX radio, I'm talking about the RX radio, also used more than 40% of the power when the node was sleeping, which is huge. So that could also be improved upon, and different methods to receive messages like that. The microprocessor power consumption was also significant when it was receiving messages, mainly because the message was encoded in Manchester format and the decoding algorithm was implemented in software. So this made it flexible. We could change the baud rates for reception and things like that, but it uses a lot of power because the PIC microprocessor that we use spends a lot of time actually just doing instructions by instructions to process the message. So what would be a good idea for this is to migrate to a specialized functionality module, or maybe a custom finite state machine to just deal with only parts that would have to do Manchester decoding. The buck efficiency, that is to say the part of the power management module that provided energy to the node, was also very inefficient when the node was sleeping, which did not help for the sleep current from the point of view of the system. One thing that would also be nice is to also consider things instead of at a node level, at a higher level. So by that I mean we're talking about having several nodes and improving the SDR interface, maybe to be able to talk to several nodes at once, and actually, maybe, I don't know, maybe do some graphs or some plots of the, what do you call it, the measurements, so that we can see what is happening with several nodes in the environment. So I would like to thank you for your attention. Are there any questions?
Thanks a lot, Mr. Nicot, for this presentation that shows the different contribution of your work. We can start now the session of the question. I propose to start with the different reviewer. I propose that Mr. or Professor Murabasi Sharia, you can start this session.
Okay, hold on just 1 second. I will, there we go, switch so I can see the reviewer. And, oh yeah, for this, let me just move so that it will be simpler for me to look at the screen. I'm just hoping that the VGA cable will stay put. All right, we're good. Okay, make that big, and I am all ears.
Okay, Thank you very much for the presentation and the nice work that you have done. I have some questions. One is when you look at your RF energy harvest or operation, have you
Yes.
looked at proximity effect? That is, if somebody walks close to the node, would that affect the performance of the node or not?
Oh yes, oh yes, I saw that a lot. Oh yeah, when the test bench in the lab is next to a room where people come in and out, that's one of the reasons we also had a lot of false wake-ups because and we had to actually put a high-pass filter on the radio demodulator, because when people would walk by, the wake-up radio would think that, oh, there's data coming in. And as for power levels, yes, we saw fluctuations in how the speed at which the capacitors would charge if people walked in and out. So yes, there is some effect to that. Yes, that is problematic.
And have you think about, or how do we resolve this or make the performance sustained in the presence of other people in the room?
Yes, so that is a quite complicated question indeed. In terms of solving that, we did not investigate that as much as we would like to, but maybe having several base stations could, which is maybe not optimal, but it is a solution, could flood the node with more energy than it needs. Otherwise, this would, if it cannot be solved, we would have to maybe constrain the node to certain locations. Maybe using directive antennas could also be a solution. That way, if somebody passes around the direction of the antenna, it would still work, but that would require nobody going in front of the antenna, and it would also limit the deployability of the nodes, as every time you would have to configure the antenna.
Mm-hmm, mm-hmm. So yeah, would you think multiple antenna would help, or?
Yeah, that could help. Maybe that way there would not be necessarily the same effect in the different bands. As seen in one of the work that I have looked at. Let me try and get back to that. This work, yeah, there were several different sources used. So I would imagine that if several different frequency ranges are operated, that the effects would be less if the environment changes around the node.
Mm-hmm, mm-hmm. Oh, that's great. Another question again regarding RF power. Have you looked at the safety limits? That is, how much power can be, or the standards allowed to transmit in that
Yes.
particular frequency band?
The 900 megahertz band?
Sure. Yeah. I mean.
Okay. So the power that can be transmitted is relatively low. I mean, we're talking about from the antenna isotropically, sometimes 10 milliwatts, in other places 100 milliwatts. And there is a very, very small niche at 869.5 megahertz, in which, at least in Europe, you're allowed to transmit at up to 1 watt. Or no, 30 dBm, yeah, that's 1 watt. So that is possible. Also, I think that in the US regulations, I'm not certain, that regulations are a little bit more lax in the 2.4 gigahertz band. So that could also be something to look at. But generally, since we were using Nicot's components that were not very efficient, especially the power management units that were, dare I say, tortured during this work. Hold on, I've lost my train of thought. Oh, yes. They were inefficient. So that would mean that in order to reduce the amount of power required by the node, if we use more efficient devices, that should reduce the amount of power that is actually needed to be sent. For the purposes of this work, we used a 1 watt power source in the 900 megahertz band. So it is possible, but it is a constraint for the moment, yes.
And then did you look at, so what is the maximum distance with taking those things into account, those limitations into account? What would be the maximum distance between your transmitter and the receiver?
All right, we've tested that. Okay, granted, we were using directional antennas, but maybe 3 dBi on each end. It operated in the room, let me think, how much distance is that? That's probably about 7 meters, 8 meters. The recharge time was very, very slow. I mean, there was probably an hour or two, if not more, between measurements. One of the reasons I think it worked at such a distance, maybe it was up to 10 meters, was not because of the power source, but because of multipath. I think that the signal was moving around in the room and recombining into hotspots around certain areas, because when the node would be moved slightly forward or backwards, then it would stop charging. So that could also maybe be used to our advantage, but it would be complicated because we'd have to model all that, and that goes outside of the scope of what I know.
Do you think you were talking about multipath and inside the room? How about outside? If you use this in environments like free space, would that?
Yeah. Outside, that would be a lot more complicated. I would be guessing that if it was outside, that maybe the node would not move around so much, like maybe if it was measuring something in an agricultural field or something like that. So it might be more conceivable in such a scenario to use more directive antenna, or maybe to rely a little bit more on solar harvesting. Generally, if something is, I'm thinking that it all depends on human activity. So generally, humans, where they live inside buildings, or maybe in very dense urban environments with lots of, what do you call these, objects in that environment. So that could be used for our advantage when things are moving around and having non-directional antennas. In something that maybe where there's not a lot of things, maybe out in the countryside or something like that, maybe the node will not move around so much, and therefore it could be have a directional antenna. Again, that is just conjecture.
Okay. One last question here. In some of the boards that you have used, the PCB boards, there are some, on the board there is a red wire somehow, like you bypass something. Can you explain like the figure 65 and, for example, figure 73, if you look at them?
All right, that would be for the radio demodulator. Let me see, where are we? We'll get there. Let me get there. I think it was a little bit higher. There we go. And where is the mouse? The mouse is here.
There was a comparator, I guess, and also...
And we are there, yeah. That one?
Yes, yeah, and there is another one as well, but let's say this one, yeah.
All right, this one, okay, that was basically a design mistake, so that had to be rectified because if not, it would not work. Basically, in this instance, I am dragging power to a bunch of resistors. This was actually the implementation of the high-pass filter, or at least one of the first versions, because this is when we had the issues with people walking by and getting false messages, which was frustrating. We had to solder I soldered the resistors to get the problem solved fast, and then drug the power wire, because with a high-pass filter, there are capacitors on the input, so it was basically making the comparator act up. So I put in some polarization resistors, that's how I like to call them, and I had to drag VCC to them.
Okay. Thank you very much. I'm good for now. Thank you.
Thank you.
Okay, thanks a lot. We can now give the hand to the other reviewer, Professor Fritz Vincent.
Thank you, Mr. President. And first of all, I would like to congratulate you, John, for the very clear presentation that you made and it's a presentation that fills a few gaps that appeared in the manuscript, so congratulations for that.
Thank you, sir.
Also, thank you very much to Thierry for inviting me to review your PhD thesis. I also have a few questions, not that many actually, but still. Well, one thing that has been mentioned, of course, this system has been built with off-the-shelf components.
Vincent, just 1 minute. We don't hear you that much. I don't know if there is any problem with your mic or something, but this is a very...
hang on.
We can hear a lot of noise now. Yeah, it's getting better. Go ahead.
Can you hear me better now?
Yeah, it's better.
Yeah, that's good.
Okay, so sorry. So once again,
No
congratulations. Of course, you built your system with off-the-shelf components.
Yes.
Which is on the one side an advantage because there are off-the-shelf components, but the downside of it is that they're not optimized, as you mentioned it. So have you considered looking for different manufacturers, different kind of, what led your choice to these very specific components?
I think I can sum that up somewhat by 2 words, brute force. Brute force, I mean spending hours and hours and hours looking at manufacturer web pages and then seeing, oh, has this guy got something better, or has this guy gotten something better, et cetera, et cetera, et cetera. Basically looking at specifications and trying to see who has the best specification for what I need. That's what led us to use, for instance, in this work, it was the BQ series, I think it was from Texas Instruments, to do power harvesting, because they had a very low voltage input at which they could start operating. By low voltage input, I mean that generally sometimes the voltage that is delivered by the power generator modules is low. So the boost converters would not start operating if it was below a certain voltage. So that was useful. Then, yeah, that would be it for the power managers. We were talking about the power managers, right?
Yes.
Yeah, okay. The thing is also, things tend to change fast. I mean, since this, I think about way into the writing of the manuscript, I got some news from a colleague about I think it was a French company called EPs, which has made some ICs that also do power harvesting that seem to be a little bit better. Unfortunately, we have not had the time to try them out, but they do look a little interesting. Maybe might be able to gain 1 or 2 dB there. So it was hard to find COTS components adapted. It was basically you keep on running around, but at some point you actually have to do the work, right? So
Exactly.
at some point, yeah, at some point we just said, okay, we're going to take these and they're going to work, and if they don't work, we will make them work.
Yeah, right. Thank you. So another question is, so you design modules that you interconnect, that you assemble together. And one question, when I saw the picture of it, why connecting them side by side instead of maybe you could have, I don't know whether it's pertinent what I'm asking, but
I see what you mean. Yeah,
stacking them one onto the other, you know, in order to maybe to gain stability. And is that something that you've considered, or is that a deliberate choice to have it, you know, on one surface? Yes, like that.
Yeah, hold on, let me get it on the screen. There we go. In terms of deliberate choice, I really didn't, okay, if we look in the rightmost figure, if you look at the power management, it's stacked there because the easiest way to solder the Schottky diode to the, between the capacitors. Generally, I think I like, well, I don't know if that works that way, but I like flat things, or I like things that I can see the whole thing. So I decided, oh, it might not just be bad to plug them in, like kind of like a jigsaw puzzle in essence. There are probably different ways to optimize how to put them together, and I agree with you there. Maybe a flat layout wasn't the best because it does consume a lot of surface area. But yeah, something that would be stacked would be nice. I mean, I even thought at some point about making a board with little small pluggable modules in a like stacking up with each other, but it would be a little bit more complicated to route all the signals because the signals on the edge of each board aren't the same. Like, I mean, for the rectifiers, we have voltage output and ground. For instance, there's only 2 pins. Whereas for the microcontroller, we'd have different digital communications. I even ended up sometimes making several iterations of a board that would have different pinouts, especially for the functionality module, so the microcontroller, depending on the sensor's digital interface.
Yeah, well, my question was quite orientated because when you look at a flat system like that, you have more surface and you're more liable to get parasitic signals.
Yes.
Might that not be a reason why you got so many falls, wake ups? I don't know. It's an ingenious question. I don't have the answer to that.
Well, I'll be honest. I don't have the answer to it either, but it most certainly cannot be ruled out. We did think about making more compact versions, and I actually have a Gerber layout that's sitting somewhere on my computer with the whole node condensed into a small circuit board. Maybe that might solve some of the problems. I mean, we don't know. I mean, we have to try it to figure that one out. But yeah, that's a very good observation. It would be nice to try that out. Yeah.
Yeah. All right. So still talking about the off-the-shelf components. As it turns out, well, without any surprise, the most consuming part is the RxTX module. And when you look at the protocol, the amount of configuration bits that's required compared, the ratio between the actual useful data, the sensor data, and what surrounds these very small. I think it's 28 bits data, and you have I don't know how many. 3 or 4
that we were sending
bits for the protocol. So is the protocol something that you have to deal with because you have no choice, or is it possible maybe to think of a lighter protocol that would be less greedy in terms of power consumption?
Well, the advantage of the transmitter module that we used is that it is fully configurable. If I be honest, it was more of a time issue, whereas I got it working in default configuration settings, and it worked. And then since there was so many things to do, I just went on and did other things. Since it was also a punctual use, at some point I think I was a lot more interested in decreasing the sleep current than I was in maybe optimizing the measurement between intervals. So I did neglect that aspect a little bit, but the module can be configured. You can choose the number of sync bits, the preamble bits. You can also change the message size. We could have used less 1 byte instead of maybe 3. And you can also remove the CRC, but the thing is really configurable. I mean, you can pretty much bit bang modulation through it. It's a pretty nice little transmitter module.
Yeah.
But yes, I do agree with you. It was something that was a little bit neglected.
Yeah, okay. So once again, I'd like to congratulate you because this is very useful for the community. Such studies. I've been looking for studies like that because I'm myself into energy harvesting for IoT. Not RF, but piezoelectric, but still, it is very useful. Now, what I'm very interested in, because I'm an ASIC designer, is if now you had to, because this is a study that that's very useful in terms of identifying what are the most power greedy parts. And now if I considered integrating this kind of system onto an ASIC, what, according to you, would be the priority, the top priority module or a part that you would consider optimizing for an integration?
In order, that would be at least, first of all, the power management unit, because I've seen papers where they do better power management units that are more efficient. That would already, especially for instance, considering the buck efficiency. I mean, we're talking about an efficiency of around 10 to 20% when the node was sleeping, which basically increases the power consumption artificially by 5. So that's a big number. So I would go with the power consumption module first. Then second, I would go with the demodulator and the wake up radio part, because it also consumes some power when the node is sleeping, which is non-negligible. And at the same time, basically also change maybe the protocol or see what can be done there. And maybe third, but that I'm not very sure about, might be the rectifier aspect. Maybe second, third, I don't know. I'm having conflicting thoughts about that one. Because, okay, the problem with rectifiers is that the Schottky diode, it's a pretty mature technology. I mean, it's been around for a long time, and it's basically the law of diminishing returns, right? The more we're trying to improve it, the less margin we have to improve. And so basically lots and lots of work is only going to improve by increasingly less amounts of percent. I mean, at some point, semiconductor physics and threshold voltages are basically going to say, oh, you can't do much better than that. So yeah, I would place it in order: power management unit, maybe rectifier and wake up somewhere on the same level, but definitely power management.
Yeah, I agree with you. The rectifier is probably not the top priority in terms of. You're right, especially when dealing with a radio frequency. In low frequency systems, like in piezo, you can still switch to active rectifiers, which are very efficient. Anyway, that's not the point here. One last question, and then I'll be done. Let me just check my notes. What was it? I'm sorry.
Oh, no problem.
Oh, well, probably it was not an important question, but yeah, let's keep this last question. It was probably a silly question. So once again, congratulations to you, and thank you for the president, Mr. President. I give you the. It's to you now.
Okay, thanks a lot. Now I propose that Mr. Meneken Jan, you can ask your different question.
Thank you very much. I understand the whole lot of work you've done and the choices you made initially, and you of course you make some choices and you build from that. But after 3 years, you've discovered stuff, you've learned things. In hindsight, what would you have done differently, knowing what you know now?
That can be a very, very long conversation, but okay. To shorten it up, first of all, I probably would have spent less time trying to optimize some aspects. I think I remember at some point my thesis supervisor had to yank me out of a moment where I was basically trying to optimize the code for the microcontroller to death, and it was taking too long, so we had to just go do something else. I might have revisited the modularity aspects, just as the previous people have stated, previous members of the jury have stated, that could be better optimized maybe to avoid interferences and things like that. I most certainly would have also spent some more time on the simulator. To be honest, the simulator, it happened more later in the thesis and was basically a result of me getting very tired of measuring supercapacitor discharges because they're very, very long, and monopolizing lab equipment to measure discharges, it was very annoying to have to leave something running all the time. So the simulator was developed in order to say, okay, we know that it takes this amount of time to discharge and we have this amount of energy available. So let's just try and simulate it so that we can test it. And then when we really need to test it, we test it. So I probably would have worked more on the simulator because it is modular, but right now it's modular through copy paste, which is still modular, but a little bit harder to set up. Another thing I probably also would have improved is maybe, let me think for just 1 second, and if nothing else comes up.
If I may interrupt you briefly.
Yes.
I hear a lot about technology and stuff, simulator, but I was thinking more in the sense of system aspect. What would you change
system
in the
aspect.
system? Yes, there are some choices been made system-wise that I may or may not agree with, but it's not my problem. But I wonder, knowing what you know now, what would you have done differently on the system side?
Okay, by system you mean taking the node and what we do with the node?
For example.
Okay.
For example, one thing that shocking is a big word, but that surprised me is that you have an on time of 30 to 50 milliseconds, if I recall correctly. That's a whole lot of time for a node that does almost nothing. And if I understand it right, it comes due to the fact that your microprocessor is underpowered because it spends a lot of time decoding Manchester.
Yes.
There are now. I understand why you choose a pig because it's common and it's easy and whatever you want. But,
yes.
But if you would have taken, for example, a modern family ARM, you would not have higher power consumption, but it would execute 15 times faster. So your overall power consumption would go way down.
It would, but one of the problems also, I understand where you're coming from, and granted, I do agree with you that the more time goes on, the more efficient microprocessors exist. Especially, yes, I know how good ARMs are. I mean, they're in phones. They're going to be, I think, in Apple's new computers, and they keep on saying things about power consumption. I mean, it's very impressive what they do, and I believe they're also optimized to really use as little power as possible.
Indeed.
One of the reasons was simplicity, because I was more familiar with PICs than ARMs at the time. So yeah, that's okay. That was maybe a poor architectural choice, but it was still a choice.
It's a valid reason.
It's valid, yeah. The other thing in terms of microprocessor performance would be one of the problems that we had was with the rectifier. Data speed sometimes was a problem. Because of the capacitive nature, sometimes data would not feed through, or the sensitivity would get worse as the speed went up. So it was basically a compromise. I mean, because I did try, one of the things that or the nice things about at least making a software implementation was that we could change the baud rate speeds, reception. So yeah, we managed to have lower reception times, but then the problem wasn't so much, the problem would become that if the node was several meters away, it would receive the power, but not the message.
But is the speed of reception really your problem in this thing?
Yes, I would say that it is problematic because the node operates or it consumes a certain amount of power when processing the message. The faster the message, the less it stays there, and therefore the less power it consumes. And I agree with you.
I'm going to be difficult. Huh? It's.
Oh no, not a problem. I enjoy difficult
Wait, I
questions.
haven't started it.
Okay.
Indeed, you could optimize by having a faster transmission and everything. But if I recall correctly, your main power drain is actually happening when it's off, when you're not doing anything. You have your wake-up sleep, you have your leakage of your capacitor, and you have about a third or something of your power going into your receiver.
Yeah, the wake-up radio, yes.
Receiver. For example, one of the things you could have done is to not power it up and just listen for a message when you've transmitted.
Listen for
sleep in between.
Yes. I see what you mean. Yeah, basically, well, I did actually implement a debugging command to shut off the comparator. The problem is that when you shut it off, it would not turn on again, and I could not figure out how to make an easy solution to have it turn on once it received a message. I mean, maybe we could have actually put the wake-up generator maybe outside the comparator, but the problem is everything depends on the comparator. But yeah, I do see what you mean. It is a power drain issue, and there probably were ways to better implement the actual wake-up part. But yeah, I didn't think about that too much, I'll be honest.
Okay. No further questions.
Okay. Thanks a lot for your question. It's time to me to ask some question too. Can you show me the slide number 20, please?
20? Okay, let's go to
the first question.
And here we are at 20.
This is some question of the processing part.
Okay, so
in this slide, you explain the ratio demodulator.
Mm-hmm.
You explain that you consider OOK or ISK modulation mapping scheme. Can you explain why you have chosen this scheme, this modulation, this mapping?
Okay. So basically, rectifiers, what do? They turn RF into DC. So that means that if you're sending anything that's phase modulated, it will be destroyed. Same ways, then in that case, well, why don't you use frequency modulation? Well, same reason, it will be destroyed. I thought about using maybe FSK, but at very far distances, but then the sensitivity would get picky. I thought about using filters, but then that would get really complicated. So ASK and UUK was a nice compromise. I mean, also a lot of the other literature uses that because with UUK, rectifier on, rectifier off, voltage, no voltage, data slicer, normalize, it's good. With ASK, on top of that, you can power the node and send messages at the same time. So that's also a good idea. So that's why we stuck with that. But we did think about modulation, and when we had issues, we thought about how we can change the modulation. But yeah, we stuck with that because it was the best solution, at least in this work, for this work.
Okay. Now, can you show me the slide 25, please?
All right, 25, there we go.
Yeah, in this slide, you present the message format. When I try to do the data rate, means the number of bits for the data and the number of bits for the control, there is a very low data rate. It's less than half. It's not possible to increase this data rate to maximize the number of bit of data by comparison of the bit of control.
Yeah, it's possible to increase the data rate. I think the module goes up to 500 kbps. So yeah, it can be very fast. You can also change the length of the preamble.
Yeah, because the number for the control is very
Yeah, I know it's huge. As is the sync, and then the message and the CRC. The CRC might not even be necessary given the distance. But yeah, it was time. I basically got it working. It was one of the last things I got working, and to make sure we had reception on the computer, you would have to change parameters. It is possible to make it smaller and to make it use less power. But then one of the aspects of this work was also more to look at things from a scenario point of view and a system point of view. So yeah, I mean, I still see plenty of things that can be changed, optimized, like changing microcontroller families, looking at different ideas, things like that. The problem is at some point it has to end, because if not, I could spend decades doing this. And in the meantime, things change, and so it's a never-ending game of catch-up.
Okay. Slide 27. In this slide, you present the system model. There is, you can give the different information on the left part of the slide. I think so. There is the memory. You have chosen RAM memory type.
Yes.
But you don't give the information of the size of this memory. How many?
The size, 128 kilobytes or kilobits. I'd have to look at the data sheet to remember well. I remember the part number, MRV45V100, I think. It's basically just a little FRAM module that works through SPI. You can store enough data for measuring things in one day, not a problem. For the moment, I've only implemented the ability to, due to the way it processes the message packets, it can only read the first 16 and less bytes or write to them. But yeah, it's possible. I mean, yeah, even for data storage, if the PIC would go off and then lose information on where to store, you could even write data in the FRAM to tell it where to resume from. I mean, there's plenty of ways to deal with it. One of the reasons also we chose FRAM instead of maybe Flash or EEPROM was lesser power consumption. FRAM is basically, I think it's ferroelectric RAM. I'm not sure of the details about the technology. I believe there's something ferromagnetic in the IC where it can be stored. It consumes less power. It has a very, very long storage life. So why not?
I have a question for this. The next slide. The next slide. This slide you present your wake-up algorithm. For the moment, you have only one node with a communication with the system. But if you have more than one node, is it necessary to have an identification process to wake up the good node in the network?
Are you talking about the address?
Yeah.
So that would be this guy.
Okay.
Yeah.
The size of the address?
For the moment, it is 1 byte, so you can address 255 magnificent nodes.
Okay. Yeah, but you have the process to identify a node with an address. Okay.
Yeah.
My last question is about the main challenge. The main challenge is the integration of this work.
Yes.
There is a previous question that you explained the different model, but what is the more challenging model to implement?
Ooh.
Not the more interesting in terms of power consumption, but the more...
Yeah, the most challenging, I would have to say either the wake-up radio, because of just getting it to work and making it power consumption, and choosing the right protocol and figuring out how to do things right. Because for rectifiers, it's standard. For sensors, it's standard. For transmission, it's standard with COTS. But getting the wake-up radio with your own custom protocol and figuring out what to do and when to do it, that's complicated. And maybe also the functionality aspect, because there's just so many microcontrollers available, and it's really hard to just pick the right one and then stick with it. Because at midpoint, I felt like changing. Sometimes I said, oh, maybe I want to use an MSP 430 because it has some more interesting functionalities. But yeah, it's it's hard. I'd say wake up radio, then microcontroller.
Okay. Thanks a lot for your presentation and your different answers. Now it's time for the supervisor. First, I propose that Madame Fadel.
So first of all, John, I would like to congratulate you for your presentation. I really appreciated the animation that you've written and make it very clear and dynamic. Congratulations also for the manuscript. It is very well written and well structured, and I wanted to underline the good balance there is between each part as well as the effort of synthesis. So, which makes reading easier. I also come back to the scope of the work. So you took up many challenges to achieve the objectives. And today, thanks to you, we are proud to show the results today and to value the results today. So for all of this, John, I want to say thank you.
Thank you.
I don't have any technical or specific question, but I want to know just some aspect of perspective. I've been working since 2012 on RF energy harvesting, but rather by developing the antenna and the manufacturing technology. In the previous thesis, we have demonstrated the capability to implement rectenna on flexible substrate in order to have a conformable or wearable system. So my question is, in this case, in this way, do you think for your node, is it possible to implement on flexible substrate? And if so, what are the most challenging or even blocks you could identify?
All right. For anything that's flexible, yes, of course it is possible. I mean, they have flexible solar panels that exist today, as well as flexible antennas that are entirely possible. The biggest challenge with anything flexible and COTS is that COTS take up a surface area and have to be soldered somewhere at some point. With one or two COTS components, you can probably, I know there are techniques to get components soldered onto Kapton or other flexible substrates, but the problem is when you have a lot of them. Because then, when you bend the antenna or solar panel or solar antenna or something, we can call it that, then the components might decide to pop off and take a little trip, which is not something we want to happen. So I would say that the biggest issue is that. And that's one of the more interesting aspects of where ASICs can come in. If everything's on a single small chip, there's a lot less chance that the components will go flying. You put a little blob of epoxy, I guess, or something, and it'll stay there. Whereas with lots of COTS components, you can't, I mean, unless you're willing maybe to grind them down and do some, let's just say it, hacks to make them smaller, it's going to be hard. But it is possible.
I have another question concerning the optimization of the node in terms of first deliberation and second performance. I mean, do you have ideas or ways to improve or perform this type?
Could you just repeat the question? I didn't hear.
I would like to know if you have a reflection of optimizing the node in terms of autonomy or integration.
Oh, of what we could do to improve the autonomy?
Yeah.
Oh, two ways. Reduce power consumption, three ways maybe. Power consumption, waste, and the amount of time spent operating for an equivalent functionality. These three things, the more you whack at them with the hammer, the smaller they get and the more the node can do things and be more compact, smaller, and more flexible in terms of what environment it can submit to.
Last question. If we use multi-sources by combining thermal or mechanical vibration,
it does add constraints. I mean, it's always possible. I mean, the more power sources, the merrier, right? The big issue, I'd say, is that for every different power source, you have to maybe add a power management IC. So that could be a problem. I've seen, I think, one of the works that is in the thesis manuscript in reference as another work to be compared to. There is somebody who actually attaches in series the solar panel and rectifier. So that can bring some interesting scenarios wherein you only need one power IC, but then the IV curve for MPPT has to be well characterized. Granted, you could also daisy chain lots of different sources or maybe put them in parallel. The only problem might be that the IV curve might get weird or they might start affecting each other. So generally, most devices, I think they only have a single curve, IV curves only have a single curvature or a simple. If they get more complicated, the MPPT might lock into the wrong region. So maybe that could be optimized if you characterize your device by having some sort of intelligent controller that knows what the load is and therefore can pop it in and out as required. But yeah, the biggest issue would be probably MPPT and making sure that maybe if you have maybe daisy chained a rectifier and solar, if the solar is off, is that going to permit RF power to go through?
So I'm done. I wish you all the best for your future.
Thank you.
And I really appreciate the time and your expertise in this business. So again, congratulations.
Thank you very much.
Thanks a lot. Finally,
Yeah.
Mr. Terrorist.
Thank you, Mr. Chairman. First of all, I'd like to thank you, the two reviewers of the thesis, Shayan Rabashi and Vincent Frick for their very good report and their very wise advice. And all the jury members that were today attending this board, and the very interesting and nice discussion we have together, because of course, as you know, we can always bring things a little bit further, even further, and we need new input, advice to rephrase things. John, what a journey. That was a very, very, very long journey.
Yeah,
Not today, but since the very beginning we started together, because we started 6 years ago.
Yeah, 5, 6 years ago. Oh yeah, I think calling it a journey is an understatement.
Yeah. So we started collaborating together before the PhD, of course, and I remember that you were doing already a very good job, and I tried to convince you to go to the PhD, but you didn't want to do it. And I remember that you've been the first one to decide the topic you're going to work on, and that was very fun. We designed the topic for you, John. And that was very challenging because we start from nothing. You start from nothing, and we didn't really know if it's going to make it. I mean, that we can do something, but we did not expect any performance because at the time there is like not really results in the state of the art that convinces that it's going to work. And during almost 2 years, you work like in a scientific cave, your cave. I mean, at the lab, of course. But, you do your job, and day after day, things pop up, and problems pop up, solutions pop up. But you make it, and I remember that very day that you assembly everything, and we were just looking at the things with only an antenna, and the power going to the antenna, and it works. And we get just the temperature of the room, and we are very happy to have it.
Yeah.
And I really thank you for this very good job. And
thank you.
And of course, beyond the technical skills that are obvious for everyone here, because you help a lot of people in many things, not only in lecturing. You have this human quality that you're happy, very funny actually, and ironic. We have this in common, and many times this ironic part saves us because we have so many problems that most of the time when we're at the very low point together, we say, okay, let's be ironic and try to solve it. And at the end, we have the very beautiful things that also exhibit very good performance in my point of view. Of course, we can improve. We can always improve things. But you made it, and I really appreciate the guy you are, what you also bring to me in terms of support, in terms of everyday life, science, and discussion we have together, well beyond the knowledge you develop. That's already a very big thing. So thank you and my best congratulations for that.
Thank you,
I
sir.
talked for a long time about you, but okay. We got the chapter today. I hope we don't close the book. We still have some lines to write, some pages, some publication, by the way. And I wish you the best for the future because you deserve it, definitely. And if I can help you to get it, no worries, I will be there.
Thank you so much.
Thank you. Thank you.
Okay, thanks a lot, Mr. Paris. Now we have to do the deliberation session. For this step, you have received an email with a Zoom link on now.
So for the members of the jury, you switch to the Zoom link and you just let us a couple of minutes to change the room.
We have to change the room.
Okay. But you can say on the YouTube, we will be back in 15 minutes.
It's okay for everyone? Yeah. Vas-y.
John,
Oui.
le mic est...
Oui, ils sont allumés.
OK.
Ah, yeah. Oui, il y a un souci là.
Ouais.
Hold on, there's a technical problem.
Okay.
There we go.
John, we have discussed and we have checked on, we have decided to accommodate the doctorate to you and for your work. It's okay. And we have read a report, a fresh report. This is a report of your defense. I will give you the different information of this report. Okay? I will switch in French for the report.
Okay.
Ok. Monsieur John Nicot a détaillé ses travaux de thèse durant une présentation à la fois pédagogique et dynamique. Cette présentation a illustré l'ensemble des contributions, tant au niveau du choix des différents composants constituant le nœud, que les expérimentations qui ont été menées suivant différents scénarios. Les réponses aux différentes questions des membres du jury ont démontré un recul indéniable, tant sur les aspects techniques et systèmes, que sur la mise en œuvre d'un processus d'expérimentation, un protocole d'expérimentation. Le jury tient à souligner tant la qualité que la quantité de travail qui a été nécessaire pour aboutir à un système expérimental fonctionnel et pouvoir le positionner par rapport aux travaux de l'état de l'art. Pour l'ensemble de ces raisons, le jury délivre à M. John Nicot le grade de docteur de l'Université de Bordeaux dans la spécialité électronique. Félicitations.
Je parle là ou?
Yeah.
Oh, okay. Okay, so first of all, I would like to thank, oh, this is hard. What order should I do this in? All right, let's do it this way. Let's do it professional and personal. Okay. I would like to thank, first of all, the members of the jury who are here today. Thank you very much for being here. This would not have happened if you were not here. I would also like to thank the jury for the questions, especially the challenging ones. It's always good to have your scientific work put into question in order to have it processed and to further in the search of truth. I would also like to thank my supervisor. It would have not been possible to get here without my supervisor. He is the most patient, single most patient human being I have had the honor to meet, since I am sometimes prone to delays. Very good supervisors, very good mentor, especially Mr. Tavis. It's just been, it's been very complicated over the past couple of years. It's been quite a journey. I would also like to thank my colleagues here at work, who also have always been present for me in times of need, as well as helping me process ideas and things like that when needed. I would also, therefore, like to extend the biggest thanks to my family, notably my parents, who have been along with me all the step of the way, as well as my extended family, both in France and outside of France. And I would also finally like to thank all my friends in Bordeaux and elsewhere who have also been here for me. And thank you so much. I don't know what to say any further.
That's already a lot.
It's a lot? Okay.
A lot of things, actually.
All good things must come to an end.
Yeah, thank you very much, John. Thank you.
Congratulations.
Line. Yep.
Thank you.
Yeah. The board, if you want to leave or give a word, there is no problem. You leave whenever you want, actually. I want to thank you once again, Shayar. Yeah. Thank you very much, guys. Thank you.
Thank you very much. Thank you.
There's one down thing about the duel is that we won't be able to drink anything together.
Yeah, yeah, we'll fix it in the future. I hope
We'll fix it up. There's a solution.
in the near
We
future.
hope so.
Okay.
Thank you, Vincent. Thank you.
Bye bye,
Have a good
Shaya.
day.
Bye, FT.
Good day, yeah.
Congratulations and good luck, John.
Thank you so much.
Thanks. Bye-bye. I keep you
Bye-bye.
posted, guys.
Yeah.
Bye. Merci à tous d'être venus, en tout cas, et d'avoir été patients. C'est l'heure de bientôt payer les amendes, non, je pense.